Hello everyone. This is a very simple demo of a very basic USB MIDI interface that I have made using STM32F103 microcontroller. This is the microcontroller port I am using, and in this board I have shorted out pins A2 and A3, which is basically the transmit and receive pins for the UART. So in this demo, the idea is from my DAW I'll send some MIDI data through the USB cable, and it will be received in this microcontroller, and those data will be transmitted to the through the UART, and then also received through the UART, and then again back to the PC through USB. So I'll plug in the board to my laptop. And here in my DAW, this is the MIDI device list. If I do a refresh, now the interface shows up here as both output and input, and I have already set up a project here. I have some MIDI data here from one of my songs, and this MIDI data is getting output to STM32, and then again in track number 4 I am receiving the data here, and then finally that data will go to a virtual MIDI instrument here. So I'll just record as well as playback so that you can hear how the MIDI track sounds. Now, if we look at the track data that got saved, here we can see in the starting section of the MIDI piece where the pace is very slow, all the data got received correctly, but still I can see at least one note got missed, and as it goes along you can see here also one note got missed, and here some notes got stuck. So overall the project does work. We can send data from USB and then to UART and then back to the PC through USB, but in some places some notes gets missed. I have put some effort there, but as of now I'm unable to get a perfect 100% reproduction of the data that is getting sent. But if you are still interested in seeing how the software side or the firmware side works to implement the USB MIDI, and so that we can get both data to and from the PC, then please check out the next portion of the video. To create the USB MIDI interface project, we'll have to follow a few steps, and since there are some modifications that we need to do on the generated files, I have this handy note on my right hand side. So we'll start from the basic, that is creating a new project. So we'll start by selecting the part number. For me it is STM32F103 C86. We'll give a project name. In this GUI, we'll start from the clock. We'll enable the external crystal oscillator, and in C-stick for debug we'll use serial-ware. And now in connectivity, this is the most important one. We can take any of the UART, but for my case I'll take UART 2 in asynchronous mode, and I'll enable DMA for both receive as well as transmit, and I'll set both of their priority to high. And I'll enable the global interrupt for this, because for the receive function I need a callback function. Anything else? Oh yes, for serial MIDI we generally have this 31250 as the baud rate, so I'll keep that. Anything else? Nothing. We're fine. In USB we'll enable USB device, full speed device, and in middleware we'll select Custom-HID. And in clock configuration, so this is a STM32F103. Here the max clock that I can have is 72 MHz. I'll select PLL clock and press enter. And the clock solver has now solved, and 72 MHz is selected. Okay, so as soon as I press save, it will generate the code for me. And in this generated code we'll have to do some modification, that is from this step onwards. In this file USB control.h, we will use a 4-byte buffer instead of 2, and rest of the things we'll keep as it is. Then we'll go to middlewares, in this file also we'll have to make the endpoint size of 4 bytes instead of 2. This is all this 4 bytes modifications are because the USB MIDI message is a 4-byte message, so that's why you are using 4 bytes everywhere. And instead of 2 arguments in this function, we'll be passing only 1, so we'll modify that. In this file we have little bit more modification than the previous ones, so we'll start from here where we're taking care of the configuration descriptors. So configuration descriptors are the descriptors that tells the host or the PC like what this device is and what this device does. So we'll remove the old example code. Also this size of the array we'll remove for now because we'll initialize, and these 2 arrays will not even initialize because our device will only work in full speed. Okay. So from where we'll get this configuration descriptor, in my previous video also I've shown, like we have this file from usb.org. So here from page number 37 we have an example configuration descriptor for MIDI. So all this data that I have written it down in a text file. Yeah. Only difference in this text file is that although in full speed transfer the maximum packet size that can be transmitted is 64, I just made it 4 bytes because that's all we need for USB messages for both the out endpoint as well as in endpoint. Okay, so we'll select this whole and we'll just paste it. And here in this list, since we are only interested in full speed, not other speed and HS, we'll just remove this and I'll just copy this. So all of them are now full speed. So it will only send the full speed configuration descriptor. And near the end, in these two functions, USB HID data out and endpoint ready, here we can see it is specifically hard coding data transfer of 2 bytes from the report buffer. We don't want that because ours is definitely more than 2 bytes, that is 4 bytes. So instead of doing it this way, we'll just simply put this. And this file is also done. Okay, and yeah, now we'll take care of the interface file. There's an application. In this interface file, we generally need to provide the report descriptor for HIDs, but here we'll just keep it as default format, because generally the MIDI USB message descriptor, it is just a 4-byte message, and that is quite well known. I think even if we just keep it as it is, operating system can figure out like what messages are getting received and what messages to transfer. So even if we don't do anything here, what I have seen, the USB device gets recognized as well as the messages get sent. So here also we will not do any modification. But here we don't need this event ID, we will only use state. Similarly, okay, so these two modifications that are done now. So at least the configuration level modifications are not done. So we will now concentrate more on main file. So we'll now concentrate more on the main file and the interface file. In the main file, so that I don't have to do anything from scratch, because this is a video and I want it to be compact. I have written all the modifications that are required here. So first things first, we need to include the custom HID header. Then in the private variables, we need to declare some variables. I'll explain quickly. Okay, so this is just just to bring the USB handle in this scope. That's it. And this TX buffer we will require to get the data from PC and store it, and then send it out as a send it out on UART. So that's why you need this buffer. And we'll mostly be dealing with 3-byte MIDI messages. That's why the size is 3. This uart-rx buffer is the buffer that will immediately get the data from UART and store it. And then whatever data we receive from here, we will store here and do the required modification, and then send it out as MIDI USB-MIDI message. That's why it's 4-byte size. And these two variables, this variables basically stores the status bytes, MIDI status bytes for TX as well as RX. And this is just a data count variable. So as we go along, we'll understand why this is required. Okay, here we'll be enabling all our DMA related functions. So for transmit, we don't need to enable anything because it's just a transmit meaning. When we call the transmit DMA, it will do the transmit and then it will go to a callback function. But here we are disabling the half transfer callback function because we are only interested in the full callback, or actually here we don't even truly need the full transfer complete callback also, because the transmit is getting called from USB events. So but for receive, we are enabling the DMA, and we are enabling the DMA in such that so the callback function will either be called when we have received all the bytes that we wanted to receive, like whatever the value we are passing here,
For now, for our case, it is just 1 byte. So once 1 byte is received, it will call the callback function. Or when our DMA, when our UART receive becomes idle for a frame time, then also it will call back our function. And here also, since we are not interested in half transfers, we have disabled it. Inside while, we technically don't have to do anything here, so we'll just put some delay randomly, because most of the our transfer will be done through interrupts. We don't have to come back to main function often, and we can do any other operation here if required. So regarding the callback function, again I have it here. Okay, in this callback function, this is basically as soon as 1 byte or the amount of byte that we require, once the number of bytes we have received, it will come back to this callback. Or if the UART is in idle state, then also this callback will be called. So in this callback function, what we are doing is whatever data we are receiving in the buffer, we are checking if that is a status byte or not, because all the MIDI data generally data means which has values, it will generally be from 0 to 7F range, and anything above and equal to 80 value is basically a status byte, meaning what kind of message it is. So basically I'm checking if it is a status byte. If it is status byte, then what I'll do, whatever next bytes of data that I'll have, I'll store it as a data byte. And if the new message that is received is just data bytes, and so we'll assume that we'll have to reuse the previous database. So this is why, because in MIDI messages, to have a since generally the serial MIDI is just 31250 baud, so considering that in modern era, at least we can consider it is a little bit slow. So to save some bandwidth, what it is done is, let's say I want to have a message like this. So this basically means this node, which is basically 64 node, is turning on because it's a 9 message, and 7F is the velocity at which it is turning on. And then immediately we want to send one more data saying 90, and the next node is also turning on, right? But generally, to save some transmission, what we will do, since both of them are MIDI note on messages, what we'll do, we'll discard this 90. So we'll send it like 90, 40, 7F, then 41, 7F. Okay, so we will not send this 90 again, but when you are receiving the data and we are transmitting it to USB, in USB mode it is always 4 bytes of data. First is related to cable number, which also we'll ignore for here because we are considering only 0th cable is there. We are not taking all this complication, taking care of all this complication here. And then 3 bytes of data. So these 3 bytes of data, irrespective of meaning if the message is getting repeated or not, here we'll always have to send like 90, 40, 7F, then again 90, 41, 7F. Here we cannot skip in USB. So we have, once we receive this 90, we have to store it in some kind of variable, and in next message, if this 90 is not received, we'll assume like, okay, it is the same status byte, and we will create our MIDI package for 4 bytes like this. This 4 byte calculation is basically nothing. Let's say if we have a MIDI status called 90, this so it will take care, it will repeat this 9, and it will look like this, assuming the cable is, this is cable number, and will repeat whatever is the MIDI status messages first nibble, and then this will make our 4th, or actually the 0th bit for our USB MIDI message. So this 9047M message in USB will look like 09, then 90, then 40, then 7F. So these 4 bytes of data we need to send in USB. So here we are taking care of that in this function, and also we are taking care of how many bytes of data we have received over the UART, because we need 3 bytes of data generally. So uh, so we are keeping a count variable here, and based on which number of data we are receiving, we'll store that value in the RX buffer accordingly. And once we have received all the data, right, we'll send it over to the USB through this function USB Custom-HID report. We'll send this buffer, and once all these things are done, we'll again re-enable the DMA receive of the UART. For transmit callback, we don't have much to do here, because in transmit the transmit event is getting called inside a USB receive event, so it will automatically be called one by one there. So once the transmission is called, technically we don't have to do anything here. We are just making it that half transparent disable, that's it. Okay, now we'll take care of the transmit side. This was the receiving side. We'll take care of the transmit side here. Here also we'll start by putting some private variables, which is so these variables are already defined in our main.c file. We are just making it visible in the scope of the file. These are basically the tx buffer size, and tx node status. And inside this function, custom HID out event, this is the function which is gets called when some data from the PC is received by the microcontroller. Okay, so here also what we are doing, once we have received the data from our PC inside the state buffer, we are checking if this node status, or meaning what kind of message this is, if we already have the node status saved. So we are saying if it is a new node status, let's say previously it was a note on message, now we are receiving the note off message. Then what we'll do is we'll save all these 3 bytes, because we are not worried about the cable number and all. So you can see we are skipping the 0th byte of the state, and we are saving 3 byte data in our TX buffer, and we are transmitting transmitting this over DMA, right? But if if let's say previous message was also a note on message, now again we are receiving a note on message. So that means this node status is basically matching. So what we will do, then we'll only send the data bytes, that is 2 and 3, second and third bytes. Actually not second and third, 2 and 3 here, it actually means third and fourth byte of the MIDI USB-MIDI message. So that only we will store it in a buffer, and we'll only send these 2 bytes and not repeat the node status byte again, like what I've shown in the paint. And one more thing is here only we are taking care of 3 byte MIDI messages. There are also 2 byte as well as 1 byte MIDI messages, as well as C6. So that is those are more not complicated, but here I have only I'm only interested in this note on, note off, as well as pitch bend, because if you consider a keyboard, the note on message, note on off message, and this control change, meaning for example sustain pedal, and then pitch bend, these are all most of the time we'll use. C6 messages and all are very I would say those are specific use cases, so that I'm not taking care of in this demo. But as from this, if I think it can easily be taken care here as well as in the receive function also, if you want to take care of the 2 byte as well as 1 byte MIDI messages. But for now, I think these messages are more than enough for most use cases, note on, off on. So we are taking care of that here, only 3 byte messages. Okay, so now I think we are ready with the code.